students. So in this lecture we will continue with our intrinsic semiconductors, and we'll see energy band, what is energy band gap, we will see. So from the first lecture what we have seen, we will revise quickly, and then we will move toward the next bit. So okay, this is the content of your module number 1, in which just introduction, what exactly mean by semiconductor we have seen. The semiconductor material, what kind of semiconductor materials are there, like silicon, germanium, so and GAS, GSP, like semiconductor materials are available. So that are available in the single crystal and compound one. Okay, so we have seen that once in covalent bonding and intrinsic material. We will see what exactly mean by, we in the last lecture we have seen covalent bonding, intrinsic material we will see, and energy levels, and extrinsic material we will see. Okay, so we know that any of the material, that is any of the device, that is we know that camera is there, then smartphones, mobiles, laptops, etc., everything is made up of that, made up of the processing unit. I am saying specifically the processing unit, like we know that RAM is there. Okay, RAM, then we know that it's having we commonly known as memory card, which that is also a type of ROM. Okay, permanent memory itself. So likewise again RAM is there, which we are using for the higher speed of operation. So different kind of devices are, transistors are there, that is in between these devices. Okay, in devices the basic is processors, and processor is made up of what you can say, transistors. So we have to learn why the transistors are made up of silicon, germanium, GS only. Okay, why we are only concentrating on the semiconductors, not with the aluminum, gold, and all that metals are there, or insulating materials are there. Okay, so the theme of the module is that we know that the lot of devices are made up of semiconductors, but why to use that semiconductors for the manufacturing of that devices, like microprocessors, the RAM, ROM, etc., etc. Okay, so why we have to stuck with the semiconductor, that we have to see. That's why we are studying the semiconductor material, then intrinsic, its properties, then extrinsic material. Okay, so this is the importance of this subject. Okay, so we have seen the silicon, germanium, in which we have seen the single crystal, like a single material, that is germanium only, silicon only. And if you are using the two of the compounds, elements we are saying, so the whatever this device is, whatever the material is called as compound, like GS, like gallium arsenide, then CDS, then GAS, then GAN, gallium nitride. Okay, then GSP. So this is GSP is used for phosphorus. We know that it is in the yellow color, so it is used for the LED, which is glow yellow. Okay, likewise we are using the different kind of material, is the GASP, GAS, likewise different kind of material we are using to illuminate different kind of lights. So next we will see, we have seen in all these themes. Okay, so here in the last lecture we have seen this kind of, this part. Just a minute. Okay, just a minute. Okay, right now. So we know that these are the group 4 elements. So we know that these are nothing but my periods, that is nothing but the row, and these are nothing but columns in the periodic table. Okay, periodic table, these are nothing but my group 4. So group 4, we know that wherever there is a same group, means group 4 elements are there, that is nothing but this is 1, 1, 2, this 2, this 3, and suppose this is 4. So 4 is nothing but the valency is nothing but 4. So this, that is nothing but the group indicate the valency of each and every material. So 4 indicate the valency of element is 4, 1. So silicon and germanium are in the group 4, that is nothing but its valence is how much? 4. So valence is nothing but what? The number of electrons are in the outermost orbit, means 1, 2, 3, and 4. We know that is nothing but the 14 electrons are there. So in the first orbit we know that how to distribute the electrons if 14 electrons are there. So that is nothing but 2n square. So n is nothing but the number of orbit, that is nothing but if how many electrons are there in the first orbit? So we have to put n is equal to 1. So 2 into 1 square is nothing but how much? 2 electrons are there. Likewise, in the second orbit, you will find how much electron? If I am putting the n is equal to 2, so 2 square 4, 4 into 2, 8. In the third, we will find 18. Likewise, it will go on. Likewise, it will go on. So in the first orbit, we know that how much electrons are there? 2. Second electron, how much? 10. So remaining are 4. So in last orbit, we have to put how many electron? 4 valence electron. Okay. So that whatever the last orbit electrons are there, we are calling as a valence electron. For example, germanium. Germanium is atomic number is 32. So how to divide the 32? First 2, then 8 plus 18. So how much? 18 plus 2, 20, 20 plus 8, 28. But how many electrons? 4. So last orbit, 4 valence electrons are there. Okay. So whatever the electron in the last orbit, we are calling it as a valence electrons. Okay. We have seen up to this. Then what is exactly covalent bonding? So in last every atom of silicon and germanium, these are in pure form. Okay. Silicon and germanium is having how much? 4 valence electron. So to complete its octet, so octet means what? Oct means 8. So complete its octet, how many electrons are still remaining? They have required 4 electrons, because it is already having 4 electrons with them. So they will share the remaining 4 electrons with the neighboring atoms. Like this one, I will show you. Suppose silicon, this is the center one silicon atom is there. So what he will do, it is already having 4 valence electrons. So he want to share, he want to complete its octet. So he will, what he will do, he will share the electrons of neighboring 4 silicon atom. Okay, so they will complete its octet and they will form it. So depending on the valency, so 4 electrons, it will, we are saying that it is called as tetravalent. If 3 valence electrons, it is called as trivalent, and 5 electrons, it is called as pentavalent. Okay. So how to remember tetravalent, pentavalent and trivalent? So I will give you one trick. So A, P, you know that this is a party. Up. Okay. So arsenic, antimony and phosphorus, these are nothing but the having 5 electrons. Okay, so 5 valence, so pentavalent, and we know that big, B-I-G, big, we know that big one. So boron, indium and gallium, these are nothing but the 3, and silicon and germanium, which is having 4 valence electrons. So can we remember this thing very easily? So how to remember? AAP, you know that that is party of Arvind Kejriwal. You can remember like this one. And arsenic, antimony and phosphorus. So it is having how much electrons? 5 electrons. Then boron, indium and gallium, that is having 3 valence electrons. So you can remember like this one, that is nothing but big and up. Okay, keep in mind. Okay, so this will share like this one. So we see in the GS structure, we know that in the gallium, we have seen like in the previous slides, that gallium is in the previous slide, that is nothing but big, B-I-G, big is nothing but the gallium. Okay, so gallium is nothing but how many electrons are there? 3 electrons are there. So what he will do, the gallium will share 3 electrons with the neighboring 5 arsenic atoms electrons. What I am saying, this is a gallium atom. Okay, gallium atom. So what he will do, he will having 3 valence electron in the last orbit. Okay, so he will share 3 with the remaining of this arsenic and this arsenic. Okay, so this will share with the arsenic, and the arsenic will share whatever the outermost having 5 electrons with the 5 neighboring gallium atom. So suppose this is my arsenic. Okay, this is center one arsenic. So 1, 2, 3, this 4 and 5 gallium it will share. Okay, so likewise it will share it will complete its octet, because you know that in the arsenic we are having how much electrons are there? 5 electrons are there. So what he will do, he will share with the other 5 electrons of gallium itself. Okay, so complete the octet and they will form and bond itself. Okay, stronger bond. Okay, so now we will see this part, what exactly mean by. So So we know that the silicon, germanium and GS we are that are the semiconductor material normally used. Okay, so if at a room temperature we, if it is in the Kelvin, so it is nothing but the 300 Kelvin. Okay, 300 Kelvin is the room temperature. Is the room temperature for this room temperature. So I have mentioned in 1 cubic centimeter, means 1 by 1 by 1. Suppose this is the cube, I will say this is the cube, 111. Okay, so yeah, if I'm taking the different material silicon, germanium and GS, so how many carriers are there? I mean intrinsic carrier means it, who will carry the electron will carry the current. Okay, so how many electrons are there in 1 centimeter cube of GS, silicon and germanium? I have shown over here in the table. So if GS is there, gallium arsenide, we know that 1.7 into 10 raised to 6 number of electrons are there. 1.7 into 10 raised to 6 number of electrons. If I am changing the material from GS to silicon, then 1.5 into 10 raised to 10 a number of what you can say electrons are there. Then if you are going for germanium, okay, germanium, then 2.5 into 10 raised to 3. So what exactly it means? What exactly it means? That is nothing but germanium is having, as compared to silicon and gallium arsenide, germanium is having more number of electrons than GS and silicon. So near about, if I am comparing the GS, this first material, with the third, so near about twice, 10 raised to 6 and 10 raised to 13. So near about twice number of electrons are there in the germanium as compared to silicon, as compared to GS. But in the silicon we are having 10 raised to 10 itself, that is the moderate one, that is the near about half of that one. Okay, so this is the concentration, means number of electrons are there. So if I want to carry the more current, so number of carrier must be there. Means suppose if I want to do one task, okay, suppose I want to shift my home from here to the Nagpur. Okay, so for that, if I want to fill whatever the material or whatever the instrument, whatever the material in my home, whatever the devices are there home, so if I'm single carrying that material, so it will require a lot of time. If instead of that one, suppose I'm having 10 number of people with me, 10 number of people, okay, so it will require less time. That means the more number of carriers will give more number of current. Okay, that is the first thing. So if you are using the germanium, so it is having how much more number of electron for just 1 cubic meter. Okay, the second thing is there, that is nothing but the relative mobility, mu n. This is a very important term, relative mobility, mu n. So what it indicates is that is nothing but, suppose silicon is having 1500, germanium is having 3900 and GS is having 8500 mobility factor. So what exactly mean? Suppose this is the place, suppose electrons are over here and they want to carry from this end to this end. So how they are moving fast from this place to this place? That is given by this relative mobility factor. Okay, mu n and mu p is there. I will tell you afterwards what exactly mean by. So this will give me, the number is high, then this will move very fast, and if this number is low, so it will take a slow time. That means if only I am having number of carriers is not sufficient for me. That is nothing but if I am having this much carrier, but they are slow, so it is none of use. So I have to choose the device according to its property. Likewise, suppose if I am using my RAM of silicon, it is relative mobility is 1500. Okay, relative mobility is 1500. So if I am using the device by using silicon, so it is having less speed as compared to GS. So that's why the GS material is used in your what? RAM. Whatever your RAM is there, that is random access memory, your mobile will operate fast. So that memory is made up of gallium arsenide. So now we will see exactly what exactly we will conclude this thing, and we will stop over here. So what exactly GAS materials are there? GAS, so number of carriers this will represent, and how fast the carrier is given by relative mobility factor itself. So today we will stop over here. So you understand the I hope that you understand the concept. So thank you very much for attending my lecture. Thank you very much.